So I am starting the presentation. Yesterday, the main aerofoil theory that was actually matched with our practical observations, right? Yes or no?
Yes, sir.
Why the lift slope or the sorry, why the lift slope is actually varying with the angle of attack? I think that particular thing is now clear to you guys.
Yes, sir.
Yes, sir.
Now, there was the typical question at the end that, sir, in the mathematical sense, we are saying it is in viscous fluid, but in experimental sense and in practical sense, we know that without viscosity, such eddy generation cannot occur at the end of the curved surface, right?
Yes,
Yes, sir.
So, in a sense of practicality, what we are saying is that for an aerofoil like this curved surface, the upper surface is having a separation. That is why at the end there is eddy generation, right?
Yes, sir.
yes, sir.
And from our perspective of streamline, we just noted it in another way that the lower surface streamline is requiring to bend like this. That is why this eddy generation, right?
Yes,
Yes,
sir.
sir.
In a sense, if I admit both the things, okay, fine, mathematically and in streamline perspective, this is the case, and in practical perspective, due to viscosity, such a boundary layer formulation occurs and such a separation occurs. See, separation is also a streamline theory kind of thing, right? What happens is actually reversal of velocity from zero to negativity. Yes or no? That I actually told you at the onset of that particular discussion.
Yes,
Yes
sir.
or no?
Yes, sir. Correct.
So it is actually the viscosity and the diffuser effect which is playing this foul part, or I cannot say it a foul part always, but making this phenomena happen that there are eddies at the end of the curved surface, right?
Yes, sir.
Streamlines are actually our perception. Streamline is not a natural thing. That is actually given by the human beings in order to realize the flow more easily, right? But viscosity, diffuser effect, these things are natural. So actual phenomena are viscosity and diffuser effect, and we are actually explaining it using streamline. That is what I told you, right?
Yes, sir.
Yes, sir.
Now there was an obvious question, sir, all these stream function and all these things what you are saying, they are actually related on a fact that ideal flow is having zero viscosity. Then how are you relating it? That was your final question, right?
Yes, sir.
I told that yes, it is correct, but as ideal flow and these particular string functions and all these things are actually allowing us to do the mathematical formulation of such flows, so people are very much concerned that the actual flow is having some viscosity, but still they are using these ideal flow formulations. But obviously that particular viscosity will have some effect on the ideal flow design, yes or no?
Yes,
Yes, sir.
So that should be taken care of in some mathematical way. in this particular discussion also. Now, what is that? That I didn't make clear to you. I just told that this particular phenomena of circulation is actually occurring. Now let's see how mathematically a circulation is given. Mathematically. See, we can actually think a circulation to be a series of small vortex along a line. That is, if the total strength is gamma, that can be a combination of a number of circulations along a line. Got my point or not?
Yes, sir.
Now let us get this particular theory of aerofoil. First of all, the circulation on an aerofoil that can be thought of a series of small circulation along the aerofoil surface. Got it or not?
So please repeat the last part, sir.
The total circulation on an aerofoil that can be thought of combination of a series of calculation Am I audible?
Yes, sir.
Okay, sorry, my connection got disrupted for a moment. What I was telling is that the total circulation on the aerofoil surface that can be thought of a series of small circulation along the aerofoil surface. Combination of all these small circulations will give the total circulation. Got my point?
Yes, sir. That is understood, sir. But you said something about the strength also. Means how can we determine the strength of the small vortex?
Coming back to that particular thing. And as now we are all thinking about the 2D phenomena, so what we make it in this way that in the direction or in the span direction, that particular thing is actually up to infinity. So that is a cylindrical kind of thing. Anyway, that is not very important. So we can actually take as small 2D circulations which are along the surface of the aerofoil. Okay.
Yes, sir.
And all these small circulations are actually combining to have a total circulation around the aerofoil. Can we think in this way? Yes or no?
Yes, sir.
Now you may ask me, sir, which surface? Upper surface or lower surface? That is a relevant question, isn't it?
Why not both, sir?
একটু জোরে বলবি কে কি বলছিলি?
So why not both surfaces? Why consider only upper or lower?
Okay, fine. Cause this particular mathematical formulation that is required to be simplified, and first of all we must take only a single surface in order to know whether this particular mathematical formulation is matching to my actual phenomena or not. Got it?
No, sir. Can you explain it again, sir?
every mathematical formulation, if I make it complicated, that won't give you an answer actually. That will be undeterminable or undeterministic case. So at the onset, every mathematical formulation starts with the most simple thing. Got it or not?
Understood, sir.
So from there comes a theory. Mind it, it's a very important theory as far as aerofoil characteristics is concerned, and that is called the thin aerofoil theory. What is a thin aerofoil theory? I'm showing you the cross section of aerofoil again and explaining it. How an aerofoil was looking like? That was having an upper surface, a lower surface, a particular thickness, and a camber, right?
Yes, sir.
Yes, sir.
Now what do you think that if I actually go on lowering the thickness, just lowering the thickness, then at one point this particular aerofoil will be a small strip along the camber, yes or no?
Yes, sir. Correct.
So we say that we can take the mathematical analogy of any aerofoil as a very thin aerofoil along its camber. কথাটা বোঝা গেছে কিনা বল?
হ্যাঁ স্যার।
Because if I take only the upper surface or only the lower surface, that cannot represent the aerofoil at all. Because the asymmetry in the aerofoil is a very important criteria, right?
Yes, sir.
And that is why we take a very thin aerofoil along the camber line and we say that is representing this particular aerofoil. Got it?
Yes, sir.
That more or less relevant in order to represent this aerofoil. So we are taking a very thin aerofoil along the camber line, okay? And as already specified, the span direction, they are infinite, so we are not considering that particular direction, so we are only considering this plane. And we are considering that there are very small vortex of strength small gamma per unit length. দেখ ভালোভাবে বুঝতে হবে। The strength of the vortex per unit length is small gamma. Got it or not? ভালোভাবে বল। The total strength is capital gamma, but small gamma is the strength of the vortex per unit length. Got it?
Yes, sir.
So again, calculus will come to help us. For a very small portion ds, the total strength will be gamma into ds, right?
Yes, sir.
Now if I say that this small portion of the total vortex, that is gamma into ds, that is inducing a very small velocity dv at a point p, which is a distance r from this particular section. I can say na, are
Yes, sir.
bol ami বুঝতে পারছি না।
Yes, sir. We can say that.
And what will be that particular velocity? As we know that the velocity induced in the tangential direction at any point is given by gamma by 2 pi r, তাই তো?
Correct. Yes, sir.
In negative sense, আর নেগেটিভ সেন্স ইজ অলরাইট কজ ওটা নিয়ে কোনো প্রবলেম নেই, that is only giving the direction. I have no problem in it. So ultimately, as the total strength is small gamma into ds, so this dv will be small gamma ds by 2 pi r. This is common, and be sincere that this is dv because this is induced by this very small portion of the vortex. এদিকের কোনো কিছু কিন্তু তাতে কোনো এফেক্ট এখন অবধি করেনি। Only this portion has induced this dv. So very good. So what is the corresponding velocity potential? Though this velocity potential won't be necessary in our current perspective, but still I am showing you because this particular thing is also going to be necessary somewhere. So what's the definition of velocity potential? Gamma by 2 pi into theta, and accordingly the small portion is inducing this particular d phi. So what is the total phi? You need to integrate it, yes or no?
Yes, sir.
So the total phi will be from a to b up to ds. Now you may tell me, sir, how can we do this particular integration? Obviously, if you are provided the geometry of this camera line and all these things, you can actually carry on the
Yes, sir.
integration. Otherwise not. But still, in this way, we can find the phi of this particular flow, right?
Yes, sir.
Anyway, now forget about phi, come back to v. What is the total gamma? That is obviously integration of gamma ds up to from the leading edge to trailing edge.
Yes,
This
sir.
is very much obvious.
Correct.
Now see this particular thing. We are taking gamma as its definition. First of all, let us take a confined path or a contour around this particular aerofoil strip. We can take it.
Yes, sir.
Yes, sir.
We are taking this very small length ds. Obviously, you can ask me, sir, if the curved line is ds, how can this be ds? As this is a very small portion, so the curvature we may omit and we can say that the horizontal length is also more or less ds. Okay.
Yes, sir.
And we take a very small normal length dn.
Sir,
Yes.
sir, if we say that ds, due to the very less curvature, ds can be taken as a straight line. So in that case, even then, why will be a variation in velocity u1 and u2? In that case, it will be same.
Wait. u1 and u2 are at dn. Wait na, কোথায় যায় দেখো আগে. We are taking a normal small length also, and that is why we are considering that here the velocity is u1 and here is u2. Okay. We are getting a confined path, na?
Yes, sir.
And we are just considering that there are 4 velocities. How the velocities will be, that will be taken care of in the analysis. Okay. First of all, we should take this particular velocities, yes or no.
Yes, sir.
Now, let's see what happens. So, by definition of circulation, what is the total circulation around it? Tell me.
Integration of velocity over the contour.
Velocity multiplied by ds, right? So, u1 into ds.
Yes, sir.
So U1 into ds, V2 into dn, V1 into dn and U2 into ds. Yes or no?
Yes, sir.
What you will take positive and what you will take negative?
Sir, when it hovers along the path, if the velocity is along the direction,
Sir, and
then it is positive, otherwise negative.
Absolutely. So U2 into ds is positive. তাই হবে তো?
Yes,
V2 into dn is positive. U1 into ds is negative. V1 into dn is negative. As per our conception, somebody can take in the other way also, but still U2 and V2 are having in this sense and V1 and U1 are having in this sense, right?
Yes, sir.
So একটা
Yes, sir.
পজিটিভ হলে আর একটা নেগেটিভ হবে, ইয়েস অর নো?
হ্যাঁ স্যার।
Yes, sir.
So here we have taken U2 and V2 dn, these are positive, and U1 ds and V1 dn are negative. We can take it. Total gamma around this confined pathway is this. Have anybody is having any problem in equation 4.5?
No, sir. It is understood, sir.
Okay, so according to our perception, what is the circulation around it? That is gamma ds. Yes or no?
Yes, sir.
That is gamma ds. So that is absolutely okay. Now you tell me that in the limit dn tends to 0, U1 and U2, they become the velocity components in the upper and lower surface of this very thin aerofoil. Yes or no?
Correct. Yes. Yes, sir.
So if dn is tending to 0, what is the value of gamma? U1 minus U2.
Yes, sir.
Now see guys. So the small gamma is actually given by U1 minus U2. Does it saying, is it saying anything?
Sir, the difference in velocity is basically equal to the is the reason for circulation.
So it is the difference in tangential velocity from lower and upper surface, right?
Yes, sir.
Now, this is not given in the text. Just you question me, that is why I am answering. Now forget about this small strip. It is correct now that the difference in velocity in tangential direction like U2 and U1, they give this small gamma.
Correct. Yes, sir.
Think about viscosity now. How a viscous fluid is actually behaving like. On surface velocity 0, then velocity is increasing, yes or no?
Correct, sir.
So there are difference in tangential velocities from one layer to another.
Yes, sir. Exactly.
And what we are seeing is that we can give by the local circulation per unit length, yes or no?
Yes, sir.
So got this analogy?
Yes, sir.
Got this analogy or not?
That was not assuming, sir, that the boundary layer thickness means sorry, basically the aerofoil thickness is very small. So, but this we have assumed, sir. So then, does it not alter with the physical means thing. Does it not alter with that? Over there, it was just for a layer without specifying the thickness. Here we have given the thickness.
Can you repeat? The last thing was not coming very
I'm
clearly.
telling sir, in that case where we were considering the boundary layer flow, sir, over there we had only one surface, so we did not consider the thickness of that surface.
That
But
is
over here,
absolutely true. But even if we think of that, see, here we are considering a aerofoil surface, right?
yes, sir.
Even if we didn't consider it, if we would have considered only this contour over an aerofoil surface, would it make any difference? Tell me. Has this particular aerofoil surface come in picture in any way in this particular analysis? I can take this contour anywhere, na?
Yes, sir.
Anywhere. That will be
Again,
equal to gamma ds.
yes, sir. So again, our derived result is u1 minus u2 is equal to gamma. But the thing is, sir,
Absolutely.
how do we assume that with respect to ds, u1 and u2 do not change?
With respect to?
Means with respect to the tangential direction, means with respect to the ds direction, the u1 and u2 do not.
That is obviously changing. We are actually assuming the very small portion ds, isn't it?
Yes, sir, but the final result does not talk anything about the ds thing, sir. It is just gamma is equal to u1 minus u2.
That is all right. So at a particular section, u1 minus u2 is given as the local strength per unit length. That is what I told. On the next section, u1 and u2 may be different, the gamma may be different.
Understood, sir.
But that can be given by this particular small gamma. That is what I told you, right?
Yes, sir. Understood.
I have given no particular numerical values. And if we think the small aerofoil is there, this small gamma is actually telling the difference of velocity between the upper surface and lower surface. Yes or no?
Yes, sir.
So got the small gamma analogy with respect to viscosity as well as with respect to small aerofoil theory.
Yes, sir.
Okay, fine.
So again, one thing I got confused, sir. In the previous day, sir, before closing, you had shown a diagram where on one side the end of the aerofoil was a triangle pattern and the other side it was a sleek pattern. So
Coming, guys, coming there only. You need not worry. You need not worry. See, here the aerofoil approximation is shown that we are considering a very thin aerofoil and we are taking the vortex heat on the camber line like this. Anyway, I am coming to that particular thing only. So, for the trailing edge, first of all, let us consider the camber trailing edge only. We are seeing that the upper and lower surface velocity should be equal, right?
yes, sir.
So where we conclude is that the local gamma at the trailing edge should be 0.
Correct.
ঠিক যে জায়গাটা এতক্ষণ করাইনি তার কারণ এটা এতক্ষণ বলিনি। You see, what are the three particular conditions? As I told in the previous class, the value of gamma around the aerofoil is such that the flow leaves the trailing edge smoothly. Then the last two. If the trailing edge angle is finite, then that should be a stagnation point, as I told you, because the two streamlines cannot cut one another.
Yes, sir.
And if that is cut, there V1 is equal to V2. So the last two can be combined. What we say, the put a condition in, wait, I think you know that these three particular conditions are summarized and called the Kutta condition, because this particular thing was actually observed by the scientist Kutta, our very well known Range Kutta, the same Kutta. Okay. And this
So my
particular,
question,
bolo?
so my question over there was, if at the trailing edge here the local circulation is zero, so then how do we get recollecting the previous day's thing, sir? Like flow over a cylinder and then extending to it to aerofoil. So then how will we get those first vertex and
Why
everything?
not, guy? Why not?
If
The
circulation
particular thing can have the total circulation small gamma, and the end condition is that you take it granted. Okay, fine. আমি এই জায়গাটুকু বলে নিয়ে আসছি, আমি এই জায়গাটা থেকে চলে গেলে অনেকে বুঝতে পারবে না। So this particular condition V1 equal to V2, that can be taken in a way that gamma at this trailing edge is 0. Is it clear to all? Is it clear to all?
Can you repeat once more?
I mean, if V1 equal to V2 equal to 0, then the velocity in the upper and
Correct.
lower surfaces are 0, and that is why the gamma at trailing edge is 0. This is clear
Correct.
to all, yes or no?
Yes, yes, sir.
Okay, fine. Now I am coming to your point. You see, we have taken a vortex sheet, right? For this particular integration, a boundary condition, isn't it? Tell me. We have
Yes,
taken
sir.
gamma ds from A to B,
Yes, sir.
right?
Yes, sir.
And the boundary condition is telling that at point B, gamma is 0. Got it? এটা হতে পারে না,
Yes.
অসুবিধা কি?
Yes, sir.
Yes, sir.
You need boundary condition in order to resolve it. Yes or no?
Yes, sir.
And that boundary condition is giving gamma trailing edge is 0. There is no problem in it. We have taken gamma along this particular A to B. That never says that at the end it cannot be 0.
Yes, sir.
We have not told that this gamma is not changing from here to here. That is why I have taken a gamma at this particular local point. That is a variable ultimately, isn't it?
Yes, sir.
Okay, so can I proceed further to the small aerofoil theory
Yes, sir.
or thin aerofoil theory?
Yes, sir. We can.
Now see, how do we actually apply this thin aerofoil theory? In previous class, you have got that from conception, it is clear that CL versus alpha curve should be like that. Right?
Yes, sir.
Yes, sir.
Now see how the thin aerofoil theory proves it. আমি দেখিয়ে যাচ্ছি কারণ এভাবে নামছি নয়তো ডাইরেক্ট চলে যেতাম, ডিউ টু দ্য ফ্যাক্ট দ্যাট ইউ নিড টু নো দ্যাট হাউ মাচ শুড ইউ অ্যাকচুয়ালি স্টাডি ফ্রম দ্য টেক্সট বুক। দেখিয়ে দিলাম। So the classical thin aerofoil theory, we start with a symmetric aerofoil at the onset. And our conditions are that gamma trailing edge is 0. And also, now the camber line is the chord line, yes or no?
Correct. Yes, sir.
So, at first we start with the camber line and we consider all the particular things are on the camber line. Then we consider that for symmetric aerofoil or for a For an aerofoil with a very small asymmetry, the camber line and chord line, they are almost equal, right?
Yes, sir.
Yes.
So we can think of this particular vortex sheet is on the chord line instead of the camber line as well. Okay.
Yes, sir.
Okay, fine. So there is one V infinity at an angle of attack of alpha, and we are considering a vortex sheet of gamma ds along the camber line, which is or will be assumed as on the chord line in case of further analysis. Now see, can we say that the upper surface and lower surface both are streamlines? Yes or no?
Yes, sir.
Because now the flow is smoothly entering the aerofoil and smoothly leaving the aerofoil, so the upper and lower surface are all both the streamlines. Yes or no? And across the streamline, can we have any velocity?
Oh, sir.
Normal to the streamline, the velocity is zero, right? So if
Yes, sir.
normal to the streamline, the velocity is zero, then we can say that how many velocities are there, guys? One is the component of V infinity, and the other is the velocity induced by this particular vortex flow. Yes or no?
Yes, sir.
So what is the
Sir.
velocity induced
Sir.
by the vortex flow? That we consider W dash. Okay.
Sir, but why is W dash? Sir, why is W dash pointing towards the normal position of the in the first diagram, sir?
W dash is not always like this. W dash can be this, but there is one component of W dash here also. Yes or no?
So, but that has to be zero then.
Yeah. Please continue.
So basically, we are taking circulation is gamma is equal to u1 minus u2. So both have the direction along the tangential direction for a very thin
That
arrow.
is all right. But if we consider the vortex here, this will have a W dash here. Yes or no?
Yes, it can.
You are considering from here. I am considering from here. These will have a W dash here or not?
Yes, sir, it will.
Convinced?
Yes, sir.
So obviously, where we are considering W dash, we are considering somewhere else the particular circulation. So ultimately, the normal component of V infinity plus the velocity induced by the vortex, that should be zero. Yes or no?
Yes, sir. Should be.
If we consider in the normal direction, this particular two velocity combination will give you a big zero, because in normal direction to a streamline there can be no velocity.
Yes, sir.
Okay, fine. First, cause 1048 already. Now what is the normal direction velocity of V infinity? We are just having a component of V infinity along the normal direction, that is my V infinity n, right? And the normal
Yes.
direction will depend on the contour of the camber line. Yes or no?
Correct.
Yes, sir.
Okay, fine. So, as per the contour of the camber line, if we consider it is point P, the corresponding slant slope is tan inverse dz dx. এটা নিশ্চয়ই বলে দিতে হবে না, where z and x are these two particular direction. Obviously,
Yes.
this dz dx will be provided to you. No problem in that. Okay. But this is the slope, right? So what is the total angle alpha plus tan inverse dz dx? with V infinity, the total angle is alpha plus tan inverse dz dx, yes or no?
Correct, sir.
So V infinity n will be given by V infinity sine this angle.
Yes, sir. Understood, sir. Sir, you are not audible, sir.
Can we consider that dz dx to be small in case of a
Sir,
symmetric or?
in between, sir, your voice has got cut, sir, for 2 minutes.
I know,
and
I know, I know, I know. I'm getting
Presentation
it
is
out.
off, sir. Your presentation is off, sir.
If we consider the symmetry is very low, so I mean it is more or less symmetry. Can I consider this dz dx to be small? Yes or no?
Correct. Yes, sir.
So tan inverse dz dx will be only minus dz dx. For small angles, tan theta is almost equal to theta, right?
Correct, sir.
And also, if we consider that we are considering only small angle of attack, why this we consider that for small angle of attack, that I will explain, but right now it is correct that our corresponding main position of this particular flight are nearly 3 to 4 degree 4 degree of angle of attack. So up to 4 degree also we can say sine theta is almost equal to theta.
So, but in yesterday's graph, we had seen that
It
significant
was up to 16 degree. Why it is not considered, that I will come later. You need not worry. Okay. Right now, just think that we are considering for small angle of attacks only. Okay.
Understood, sir.
We have not come to the extent of flight dynamics yet. That is why it is not totally clear. But still, so if tan theta is theta and sin theta is also theta, then this particular thing is simplified to the, yes or no? তাড়াতাড়ি দেখ।
Yes, sir.
So V infinity n is there. Now we must consider this W dash S, which for the case of chord line comes to Wx, right? For symmetric aerofoil, as I told you that this particular thing will come to here, yes or no?
Yes, sir.
5 minutes left. I am trying out my best. What is this Wx? As you have already told that sir, W cannot be induced from this part only. This should be induced from this part, right?
Correct.
So we are having two variables, both in the same x direction. One is for the gamma and one is for the position of W. Okay.
Yes, sir.
So we consider a very small d zeta that is equivalent to dx, but just in case we cannot actually make this particular thing cannot induce W here. So we are considering this particular small circulation gamma d zeta. Gamma d zeta is inducing this W, okay?
Yes, sir.
So what is this W? Same gamma by 2 pi r. What is your gamma? Gamma is gamma d zeta. And what is the distance r? That is x minus zeta. Right or wrong?
Yes, sir.
Right, sir.
So the dW is given in this way. I can say,
Yes, sir, we can.
very good. So what is the total W? We must integrate it from 0 to C.
Yes, sir.
Now the main question is how to get this particular integration done. Otherwise, as per our streamline theory, V infinity n plus Wx should be equal to 0. So what was our V infinity n? And this is our Wx. If we sum, that should be equal to 0, right?
Yes, sir.
And these we call the fundamental equation of thin aerofoil theory. 4 minutes left. Should we go to solve it today or leave it?
No, sir. I think we should do it on Saturday, sir.
Okay, so up to this, is it clear?
Yes, sir.
Yes, sir.
Okay, so
Yes,
we
sir.
are going to solve it in the next class, okay? But remember up to this. Remember up to these guys, okay?
Yes, sir. Yes, sir.
So up to the fundamental equation of thin aerofoil theory we have achieved. We will solve it in the next class. So
Thank you, sir.
Thank you, sir.
okay, let us stop today. Ritik, stop the recording.
স্যার রেকর্ডিং স্টপ করে দিয়েছি আপলোড করে দেবো কিছুক্ষণের মধ্যে
Okay, okay, chalo. Bye for today.